So blocking and matching are two different types of experiments. So most of the time, we're going to run what's called a randomized comparative experiment. We're just going to take all of our subjects, we're going to randomly assign them to whatever treatment groups we have, run the experiment, compare our results at the end. But there are going to be times where we cannot simply randomize at the beginning and start going from scratch. There are times where some things, some factors outside might affect what we're working with, and so we have to attack them a little bit differently. So that's where blocking and matching come in. Blocking. Here's an example of where blocking might have to come in. If we're looking at a mobile phone company, they're considering two different keyboard designs, so design A and design B, for its new smartphone. The company decides to perform an experiment to compare the two keyboards using 10 volunteers. So the response variable is typing speed. They're trying to measure how fast they can type, or they're going to measure in words per minute. So how should the company deal with the fact that 4 of the volunteers already use a smartphone, whereas the remaining 6 volunteers do not? So think about the scenario here. They have 10 volunteers. Now if we used a truly randomized comparative experiment, what we do is we'd start with our 10 volunteers and do what? Randomly assign them to 2 different groups, right? What would my 2 groups be?
Board A, board B.
Yeah. One group would try board A, or keyboard A, the other one would try keyboard B, and then we can compare typing speeds. Okay? Now, if we're looking at this, it says 4 of the volunteers already use a smartphone, whereas the remaining 6 volunteers do not. Why would that maybe cause an issue with us just taking our 10 here and randomly assigning them to the 2 different keyboards?
Because those 4 could end up in the same group, and so that group will do a lot better.
Yeah, if we have 4 people that are already using a smartphone, chances are they're going to be faster already than the 6 who do not currently use smartphones, right? So whether they're getting keyboard A or keyboard B, they're probably going to be faster anyway because they're used to how smartphones work, how they operate. Now, if I were to simply randomly select 5 from each of the volunteers into each group, those 4 smartphone users might all end up in group 1, which means when we get to the end, if they were faster at typing, we won't know if that's because 4 of the 5 already knew how to use smartphones, or because that keyboard is better for faster typing. Does that make sense? So here we have some information beforehand that we know part of our sample will probably react differently to what we're trying to do here. So before, when we felt there were major differences within our population that we were selecting from, what did we do? We stratified. If we knew there were major differences that would affect how people respond to either the question or, in this case, how they respond to the different keyboards, we stratified. Now again, because experiments are kind of a special thing, what we're basically doing here is we're renaming stratifying with blocking. So blocking is stratifying. The only difference is we call it stratifying if it's a sample survey. We call it blocking if it's an experiment, and that's important that you distinguish between the 2 there. So that is something I would definitely write down here. Blocking is stratifying in an experiment. Okay? So, with that information then, how would I actually attack the design of this experiment? What would I need to do first? Exactly. We'd have to separate the people who use smartphones already from the people who do not use smartphones already. So I'm going to put the 4 smartphone users into one group. I'm going to put the 6 non-smartphone users into a separate group. Now within each of those groups, what am I going to do from there? So what am I going to do with my 4 smartphone users? Randomize them into keyboard A and keyboard B. And what am I going to do with my non-smartphone users? Same thing. I'm going to randomize them into keyboard A and keyboard B. So within each separate group, I'm going to run the experiment as I normally would. Split them into keyboard A, keyboard B, and then at the end, compare typing speeds. Okay, so let's go ahead and take a look at what it looks like, and then we'll come back to this. So don't start writing this yet. Let's get what it looks like to start with. So we started with 10 volunteers. We're going to separate those 10 volunteers into 2 separate groups because we feel that they will react differently to the different keyboards. So smartphone users go into one group, non-smartphone users into a second group. Now of the 4 smartphone users, we're going to randomly assign them to 2 different groups. So 2 are going to use keyboard A, 2 are going to use keyboard B. Within our non-smartphone users, 3 are going to use keyboard A, 3 are going to use keyboard B. Again, randomly assigned. So now what we're going to do then is bring all the smartphone users back together. So at the end, we're going to compare, for smartphone users, which keyboard worked best. For non-smartphone users, which keyboard worked best, so which one had the highest typing speeds. And then once we've analyzed separately, we can bring it all together and see if it matched up. So maybe keyboard A was better for both groups, which means they want to use keyboard A. If it was different, let's say smartphone users were better at keyboard A, and non-smartphone users were better with keyboard B, what do you think they want to do here? Okay, they may choose option B, keyboard B, because that might attract more people to start using smartphones. So they'd have to think about their target audience and who they actually want to cater to. Do we actually want to cater to people using smartphones already, or do we want to try to attract more people to smartphone use? Okay, so then they'd have to have a decision to make. Between the 2 groups, they saw a difference, so maybe they study a little bit further with a larger audience or whatever, and make their decision from there. But that's what you would do if you identify major differences within the group of subjects that you're starting off with. Okay? This would also be something like the tomato example. So from yesterday, we talked about growing tomatoes using the fertilizer. So we had 3 different treatments. There was a full dose, half dose, and no dose. Now, let's say you had chosen that you wanted to go out and buy 30 tomatoes. Okay, so you had 30 tomato plants that you were going to grow. You were going to separate them in. But let's say the first store you went to only had 18 tomato plants. So you had to go to a separate store and get 12 more tomato plants to get your total of 30. Now, would you necessarily want to throw all 30 into the same batch and start randomly assigning them? Probably not. There may, depending on the supplier to those 2 different stores, there may be some fundamental differences between the plants that you bought. So you would need to take the 18 that you bought from store 1 and put them into a group, randomly assign them to the different treatments, and then take the 12 you got from the second store and place them into a separate group, and then assign them to the 3 treatments and so on. So that way you can meet out any differences that might actually be between the plants. You can see if there were differences there that were unforeseen. Okay, so things like that. So when we block, we're taking groups of individuals that are similar within but different between. So just like stratifying, Group A is different than Group B, is different than Group C. But the people within Group A are all similar. The people within Group B are all similar, and so on. So it's the same process as stratifying. So we're going to separate those different types of subjects to eliminate any bias. So in our group here, we have to separate smartphone users from non, because if these all ended up in the same spot, we wouldn't know if the keyboard was truly faster or it's just because those people were used to using smartphone keyboards in the first place. Okay with that? Okay. So let's do another example. This is for you guys to try. So women and men respond differently to advertising. Researchers would like to test the effectiveness of 2 advertisements for the same product. So outline a randomized block design using 300 total volunteers. There's 180 men, 120 women as subjects. describe how you would carry out the random assignment required by your design. So this is not a randomized comparative experiment. I'm not taking all 300 and separating them into two separate groups. So treatment 1 and treatment 2. I'm going to be using a randomized block design. That means I need to separate my groups first and then randomize to the different treatments. So what I want you guys to do is go ahead and diagram what this experiment would look like. Don't worry about the description of the random assignment yet. We'll talk about that together. But draw the diagram for what this experiment would look like. Make sure you're specific with how many subjects are in each group you create and so forth. All right, so let's take a look, see how you did here. So the first thing, we're starting out with 300 total volunteers. Okay, so you always start with the total number of subjects you're working with. So we have 300 volunteers that we're starting with. Now, because men and women respond differently, what's the first thing we should do with these 300 volunteers? Break them up into men and women, right? So they told us there were 180 men and 120 women. So we're going to break them up into their two separate groups. And when you're doing this, again, when you diagram, be as specific as possible. Now, right here, did we do any sort of randomization? No. All we did was split them into men and women, right? So there's 180 men, 120 women. Now, among the two different groups now, what are we going to have to do? Take an SRS from each group and assign them to one of how many treatments? 2. There were 2 different advertisements they wanted to take a look at, right? So we are going to randomize the men into group 1, which would watch commercial 1, and group 2, which would watch commercial 2. Make sure you note you have 90 men in each. You need to talk about how many subjects are in each at each level of what you're doing here. We do the same thing with women. Randomly assign them to group 1 for commercial 1, group 2 for commercial 2, so there are 60 women in each. So we split to men and women, and then within men and women each, we randomly assign to the 2 different groups. And once they've watched the advertisements, we bring them back together and do what? Compare their results. Okay? So we'd start by seeing how men reacted. So we'd compare. How did the men react to commercial 1 and commercial 2? And then how would the women react to commercial 1 and commercial 2? And then we can bring it all back together and see if there was a fundamental difference. Did one commercial work for both? Did one commercial work better for men than for women? And then from there they make their decision. So if they came back that commercial 1 worked better for men, commercial 2 worked better for women, they'd have to kind of decide, well, who are we trying to cater to? So which advertisement would we want to use based on our findings there? Everyone okay with that idea? Okay. Now, as far as the random process would go, so the way we've drawn it out here, we'd separate them in, so we have the min is 180 total people. We randomly assign it, so we label them from 001 to 180 or 000 to 179. We use a table of random digits or calculator, create 90 unique values, which would go into group 1, 90, the rest of the 90 go into group 2, and then the same thing for women. Okay, so if you're explaining your process, you need to have a couple sentences talking about labeling the subjects, assigning them values that way, and then how would you do the process. Okay? Next thing, let's talk about matching. So matching is somewhat a form of blocking. So it's used two different ways. So there's two different types of matching experiments you might encounter. Okay? One is fairly common, and the other isn't used quite as much, and we'll talk about why, what the difference between the two are. So one form of matching is essentially a blocking process. So what you're going to do is you're going to the blocking is going to happen by matching pairs of similar experimental units. So what that means is you're going to take your overall group of subjects or experimental units, and you're going to try to pair them off into similar pairs. So person 1 and person 2 should be pretty identical to each other. And then you go through that process throughout all of your subjects. Okay? If you're working with animals or you're working with plants or something like that, same type of deal. You try to grab plants that look about the same, so about the same time along in their progression, or look about to be the same amount of health, things like that. So you're trying to pair together by similarities. Okay? Now, once you have them paired up, you will have to randomize each pair. So you're going to randomly select from pair 1, one of the people is going to go into group 1, the other person is going to go into group 2. And then you continue that process throughout for each pair that you created. So when we say matching, you also see the term matched pairs. It means the same thing. So matching and matched pairs designs are the same. It's just a little bit different terminology. So this is type 1. Take your subjects, try to split them into to pairs of similar experimental units, and then separate those pairs. One goes into group 1, one goes into group 2, and you do it by random process. Okay? When we use matched pairs designs, we only use them when comparing two treatments. So if there's a subject or the type of problem where there's more than one treatment, or I'm sorry, more than two treatments, we can't use matched pairs, and we have to do something a little bit different. So matched pairs designs utilized only when there are two treatments available. Okay. Now, the second type of matched pairs, the one that's most often used. So the first one, you take two very similar subjects, they each get a treatment. That's type 1, that's the one we just discussed there. The other type, which is much more common, is that one subject gets both treatments. So every single subject in your sample is going to experience both treatments. So what needs to happen here, to try to control as much as possible, to weed out any variation that might occur when one subject gets both. So when we use this second type of matched pairs design, the order of the treatments must be randomized. So if I have 300 subjects and I'm going to use a matched pairs design, I'm either going to take those 300 people and put them into 150 pairs of similar individuals, and then for each pair, randomly assign one to group A and one to group B, or I'm going to use this second method. And in this second method, what I would do is I would take the 300 people, I would put 150 of them into group A, I would put 150 of them into group B. And from there, I would have group A try treatment 1 and then try treatment 2. Group B would try treatment 2 first and then try treatment 1. And then we bring them all back together to compare results. So in the second method, what you're doing is you're having every single subject go through both treatments that we're looking at. The only thing that's going to change is what order they do the treatments in. So you have to randomize the order of the treatments. So half of them are going to try treatment 1, then treatment 2. The other half are going to be treatment 2, then treatment 1. Now, the way this one works, this second option, is that every single subject becomes their own control group. Because now you're comparing the results to the same person. So since they're trying both treatments, your comparison is that person to themselves. How did they respond differently to the two treatments all the way throughout? Does that make sense? So when you're looking at these two, the second one is most often used because when I look at this first option, I have 300 random people that just showed up to volunteer for a study, right? I need to take those 300 people and match them in pairs of similar individuals, people I think are going to identify or react similarly. Well, how likely is it that you're going to get 150 perfect pairs of similar individuals from the 300? Not very likely, okay? Most often, this first type is used if the study involves twins. Twins tend to be very similar in nature. So you can take one twin and randomly assign them to one group and the other twin to the other group and see how they react from the different treatments. But in most cases, it's very, very difficult to pair up the subjects to get them situated with similar individuals. So the second option is usually the better option because now you know that the person's trying both treatments. That person is as similar to themselves as they can possibly be. So when we see any differences among the treatments there, we know that the differences were because of the treatments and not because of the assignment of the pairings. Does that make sense? And then the idea of randomizing the treatment order is only to weed out any other effects that might occur. Maybe treatment 1 followed by treatment 2 gets a different response than treatment 2 followed by treatment 1. And so we need to know these things because otherwise we get inaccurate responses at the end overall.
So is matching the most accurate because it's the same person?
Not necessarily. It depends on the experiment. In some cases, yes, a match pairs is the way you definitely want to go. In other cases, it wouldn't necessarily be because of time or things like that. Like if you're thinking of like you're trying to figure out if a new diet works better or something like that, you wouldn't necessarily have one person try one diet and then try a second diet later, because if they've already taken one diet, they've probably already lost some weight, which means the second diet, no matter how good it is, they're probably not going to lose either as much or things like that, or you'd have to have them get back to their original weight and then try the second diet and compare. So something like that, you'd have to just split them up. Here's one group, here's the control group, or here's a comparison. So it just depends on the situation. But yes, match pairs is a good one if you can use it. All right. So match pairs designs are typically used with like taste tests. So do you prefer brand A or brand B type of thing? So Coke versus Pepsi. If Coke and Pepsi, they're trying new formulas or whatever, they want to see if people prefer. So sometimes like Pepsi tries a new formula, so they try their old Pepsi versus their new Pepsi to see which type people like best. Or Coke might do something similar to that. Okay? So in a match pairs design, you would want the same people tasting both brands. Because if you tried to have two different people taste the same product, those two different people might have completely different tastes, right? So you want someone compared to themselves. So if I were looking at a design for this, if I was going to just do Coke versus Pepsi, okay? So let's say I start with 40 subjects, Okay? So what I'm going to do is, since I'm using a match pairs design, I know all 40 subjects are going to try both pops and give us their preference, but I still need to utilize randomization. So I'm going to randomize my 40 subjects into two groups. So 20 subjects into group 1, 20 subjects into group 2. So group 1, we'll say we'll try Coke first, and then try Pepsi second. Group 2, we'll try Pepsi first, and then try Coke second. And then at the end, we compare preferences. Okay? So this is what a match pairs design would look like. So if you're diagramming out a match pairs, this is exactly what it looks like. Take your subjects, split them into two separate groups randomly, and then have one group try treatment 1, then treatment 2, have the other group try treatment 2, then treatment 1, and then you compare. Okay? Now, some things to kind of consider on something like this too, because sometimes they might ask you to actually describe your process of running this experiment. So let's say you were running this experiment. Would you want to have basically a can of Coke and a can of Pepsi just sitting on the table and say, okay, I'm going to have you try this brand first, and then I'm going to have you try this brand second? And then someone else comes up and they try Pepsi first and then Coke second. Would you necessarily want that to happen? Why? What would possibly happen there? Okay, people already know, based on sight, which pop they prefer, right? Whether they like Coke or Pepsi better. Now, if you are showing them what type of pop they're drinking, they're already going to have in their mind, I already know I'm a Coke person, so I would like Coke better than Pepsi, right? I'm not even going to give it a fair shot to see if I like the one better than the other. So one of the things that's important here, especially with taste tests and things like that, medical studies, blinding. You have to blind your subjects. They should not know what they're trying when they're doing it, because their prejudgments will follow and taint the results otherwise. So you give them a cup, one filled with Coke, one filled with Pepsi, have them try them each, and then give the preference from there. Okay? Now, in this particular example, obviously Coke and Pepsi are so well known, people even by taste can probably tell the difference between the two. So this would be something more like Pepsi with a new formula, or some lesser known brands that people might not know or have been exposed to a lot of before. Okay? So that's one option. So taste testing, things like that. The other option, or another option, I shouldn't say the only other option, would be something like pain relievers. Knowing which pain reliever works best. So Tylenol versus Advil, you might have people who have chronic headaches. And so the first headache they experience, they try Advil, the next time they try Tylenol. And then the other group, first time they have it, gets Advil first, and the next time Tylenol, whatever, reverse the order. Okay, so things like that are going to lead us to match pairs designs. We okay with that idea? All right. So your assignment is going to be a worksheet.